Phoebe's talk, I would like all the speakers to come back down in here, and then we'll have an open sort of discussion and session. You can pose questions directly to the speakers or more general questions across all the speakers. So with that, I'd like to introduce her talk, which is Between the Footprints of Natural Climate Variability Modes. Thank you for coming to us today.
Thank you. I just hit start here. Okay. Well, thanks to Andrew for inviting me, and thanks for having me out here at OCV. This is my first time here, so it's exciting. And Andrew's invitation actually comes at really great timing. We're just getting underway on a couple of different projects looking at interannual variability in our longline fishery in Hawaii. So I'd like to give you an overview of some of those projects. And in doing that, I hope to show you that where we are in Honolulu, we're really between the footprints of a number of natural climate variability modes. So we have to look for additional drivers to explain interannual variability. And before I get started, I'll just say that the work I'm showing today is a collaboration between a lot of people, and I've acknowledged them throughout the talk on the slides. So I'll start out with a really brief introduction to the Hawaii-based longline fishery. It is a limited access fishery, and in 2015, there were 142 vessels participating. Together, they set a combined 49 million hooks over a footprint of about 13 million square kilometers. And then in terms of landings in the port of Honolulu, if we rank the commercial fishing port with other ports in the United States, we think of Honolulu as a high-value, low-volume fishery. So in terms of the pounds of fish moving through the port, we're ranked about 27th, 32nd in the United States, depending on what year it is. And then in terms of value of those fish, we're actually ranked 6th in the United States. So it's a very valuable commercial fishing port. And then if we step out and look at the larger economic footprint of that fishery, so looking just beyond the fishermen and the value of the fish themselves, the longline fishery supports almost 10,000 jobs and is worth almost $1 billion in sales impact. So we have a lot of motivation to understand what's happening with the fishery and understand how it might change in the future. So the Hawaii-based longline fishery is actually two different fisheries. There is a deep set fishery for bigeye tuna, and they set their gear a little bit deeper in the water column. They operate during the day. And there's also a shallow set fishery that's targeting swordfish, and they fish shallower in the water column and they operate at night. And these are totally separate vessels and different fishing masters. And if we compare these two fisheries, the deep set fishery is about an order of magnitude larger in terms of their effort, the number of fish they catch, how valuable those fish are. So for this talk, I'm really going to focus in on this deep set bigeye tuna fishery. And I've tried very hard to pull all of the fisheries jargon out of this talk. I realize you're not fishery people. However, there is one thing that is going to creep through across the talk, and that is CPUE, or catch per unit effort. You can think of that just as catch rate. So a higher number means we're catching more fish. Technically, it's the number of fish caught per 1,000 hooks set. And we also have a biomass CPUE, which is the number of kilograms per 1,000 hooks set. So what you're looking at here is a time series of annual CPUE of bigeye tuna from 1995 through 2015. I can just give you a couple examples of some of the questions that we're looking at our fishery. So up until 2009, we saw a declining trend in catch rate for bigeye tuna. And then after 2009, this catch rate reversed. So there's questions about whether we can expect this increasing catch rate to continue into the future, or if eventually it's going to reverse and we're going to start seeing declines again. And then another thing is in 2015, so the fishery is managed on an annual basis. There's an annual catch limit in terms of tons of fish that are caught. Once that limit is reached, the fishery is closed until fishing starts next January 1st. It's very rare that the fishery closes. And if it does close, it usually closes in mid to late December. However, in 2015, the fishery closed in August, which is incredibly early. And as you can imagine, that has enormous economic and market impacts. Then in 2016, it closed quite early again in the fall. And last I heard for 2017, we're on track to close in mid to late September. So there's a lot of questions about why we're having these higher catch rates earlier in the year, and if this is sort of a new normal for the fishery, or if it's just a temporary change and things could go back to normal in subsequent years. So in terms of the footprint of where our fishery operates, this blue box covers the zonal and meridional extremes of where the deep set fishery has operated over the past 20 years. However, the core area of the fishery is really in those two hatched boxes there. The white hatched box is really where the fishery's been the most active over the longest period of time. And then in the past 10 to 15 years, the fishery has really expanded to the north and northeast of Hawaii into that gray hatched box. So when we look at how the fishery overlaps with footprints of interannual variability, we're really focused on those two hatched boxes. That's where almost all the deep set effort is set. So we can look at the footprints of variability. We can start with ENSO. So we have the footprint there along the equator. We have the Nino 3-4 box just for reference. So you can see that the fishery is really to the north of the primary ENSO footprint. You can put the PDO up there. And if we look at the areas where the PDO is most strongly correlated with sea surface temperature, it's really to the north of where our fishery operates that signal is the strongest. We can put the North Pacific gyre oscillation up there, and what we find is where we look at where sea surface temperature anomalies are positively and negatively correlated with the MPGO index, it really slices right through our fishing area. So part of the fishing ground is positively correlated, part of the fishing ground is negatively correlated, and then right through the middle of our fishing grounds, there's really no correlation at all. So it's very challenging to try and relate the phase of the MPGO to what's happening with the fishery. And then finally, we can put the warm blob up there, since that's a big topic as of late in the North Pacific, and you can see that it's entirely to the north of where our fishery operates. So spatially, we're really between the footprints of these modes of natural climate variability. And then if we look temporally, what you're looking at here in the red and blue lines are monthly values for the Oceanic Nino Index, the Pacific Decadal Oscillation, and the North Pacific Gyre Oscillation. And then the black line overlaid on there is just annual CPUE for Bigeye tuna that you saw before. So one thing about tuna is the bigeye that we're catching are anywhere from 2 to 6 years old. So if you catch a bigeye in 2015 and that fish is 5 or 6 years old, and you want to look at how it's been impacted by interannual variability, you start with ENSO. So we know there was a big El Nino in 2015, and maybe that was important in that fish's life history. But also early on in its life history, there was also La Nina conditions. So how do you tease apart what was more influential in their life history and what might have a bigger impact on the fishery? And then you can see the same thing with the PDO. It was in a positive phase in 2015. But if that fish is 5 or 6 years old, there was negative PDO conditions over much of its life history. And then we see the similar thing but opposite for the NPGO. So it can be challenging to tease apart those influences. So putting this together temporally, the fishing ground is managed on an annual timescale, and we catch fish that live for multiple years. So that can be challenging when we're looking at climate indices that are relevant in terms of ENSO on a monthly or quarterly scale, or for the PDO and MPGO on a more decadal scale. So we have to turn to some additional investigations to try and look at the role of interannual variability in the fishery. So I'll take you through 3 examples of projects that we're working on right now. And the first looks at interannual variability in bigeye tuna catch. So one very cool thing about bigeye tuna is that we catch them over multiple years in their life, so we can watch them age and grow through time. So what you're looking at here, this is fish size along the x-axis, and then each bar here is a quarter of the year from 2006 through 2015. And then these purple bars are just the proportion of fish in that quarter that are that size. And what you can see is you have fish that are growing through time, so they're getting older and larger as you move down through time. So this suggests that if we can figure out the timing of these propagations of age cohorts, that if we identify when they start, we can get an idea of when they'll end, and we have more big, large fish. So some colleagues have developed a recruitment index for bigeye tuna. And what the recruitment index is, it's here in this blue line, and it's basically a standardized catch rate of small bigeye tuna that are less than 15 kilograms. So these are about 2-year-old bigeye tuna. And what they've found is this recruitment index peaks about 2 years before catch rates for the whole fishery peak. So you catch a lot of small bigeye tuna, and then 2 years later, you catch a lot of older, bigger bigeye tuna. So that's really helpful in kind of getting a sense of what might happen a year or two into the future. But it begs the question of what is driving those recruitment pulses in the first place. So what's happening in the environment to lead to these peaks of small bigeye tuna? So to look at that, we're looking at median phytoplankton cell size. And this can be estimated from ocean color and ocean temperature. So we can do this for the footprint of the fishery. So we're looking at annual and quarterly time series of ocean color, temperature, and phytoplankton cell size. And there's a little bit of an offset when you switch from the CWIFs to the MODIS sensor, so we can apply a correction and just align those time series a little more seamlessly. And then we can look at how median phytoplankton cell size aligns with catch rates of bigeye tuna. So I mentioned the recruitment index precedes peaks in catch by 2 years, and that those fish in the recruitment index are 2-year-old fish. So we can lag cell size by 4 years. So that's looking at the conditions of when those fish are recruiting to the fishing grounds. And we can look at how this phytoplankton cell size correlates with bigeye CPUE. And we find that at that 4-year lag, it actually correlates quite well. And so what we're thinking is that phytoplankton cell size can be indicative of food quality in the environment. So when you have larger phytoplankton cell sizes, you have greater food quality, you have higher survival, and those cohorts of fish then go on to be those big recruitment pulses in the fishery. So there's still some questions that we're looking at for this project. Foraging success is only one piece of the survival puzzle. You also have to evade predation, and then 4 years is a long time to be out there in the wild, so what happens in those intervening 4 years that allows those cohorts to propagate through? So that's the first study that we're working on. The next study that I'll talk you through is looking at multidecadal change in bigeye size structure. In size structure, it's important from an ecological perspective in the health of the ecosystem, but it's also important from an economic perspective because big fish are more valuable than small fish. So for example, if you have 50 kilograms of tuna from one 50-kilogram tuna, that's about twice as valuable as if you have 50 kilograms of tuna from two 25-kilogram fish. So there's a strong incentive to find big fish. And if you're thinking of fishing as a family business and it's something that you want your children and your grandchildren to be able to do, we want to know that that's going to be a viable job option in the future. So to look at multidecadal change, we are turning to historical studies to try and look at what fish size structure was in the past and how it relates to the present. So this is a study by Kume from 1969. He looked at bigeye size structure in the same waters where our fishery operates now. So similar to the earlier plot of size through time, this is size along the x-axis, and then it's just time averaged over this 10-year period. So we have the first, second, third, and then fourth quarter of the year in 2 zones of latitude. So on the left, we have Kume's historic data, and then here on the right, we have our data from the present day fishery. And we can compare these two, and 2 things are apparent. First, in Kume's historical data, there's peaks of large bigeye tuna, especially in this northern region north of 28 degrees north, that we just aren't seeing in the fishery in the present day. And then also in Kume's data compared to ours, what we are seeing now is a peak in these smaller bigeye tuna that weren't really present in the 1950s and 1960s. So we can start to look at what might be explaining this shift towards smaller bigeye tuna. We can start with looking at modes of interannual climate variability. So this shading on the left here overlaps with Kume's time period, and then this is the data from the present day fishery. And so if we're trying to look at the influence of either ENSO or the PDO, it's really tricky to tease apart these different phases because all these data are aggregated, and we can't go back and change how people did studies in the past. We have a little bit more flexibility here because this is our data, but then trying to align with the same climate conditions is still very challenging. So fortunately, we have other tools that we can turn to, and one of these is an Earth system model called Cobalt from folks at GFDL. And one very cool thing about Cobalt is that it's forced with reanalysis data, so it's actually representative of the actual past. So we can look at what the environment was like during these historical studies and compare it to the present day. Also, Cobalt includes size-structured zooplankton and phytoplankton, as well as heterotrophic bacteria. So we can use this output from the Earth system model in conjunction with ecological theory to look at whether changes in the plankton size structure could tell us about changes in bigeye size structure. And we do that by assigning these plankton groups to size classes and looking at abundance at size. Then if we do this on a log scale, we can fit a nice linear fit to that. And we can extend this size spectrum from the plankton community all the way out to apex predators and see if that can tell us some about the shift in size structure. So first looking just at the plankton data themselves, this is from the time period that Kume looked at, and then present day for the northern and southern region. First, we see a shallower slope further north, which is where Kume saw more large bigeye tuna, so that seems to make sense. And then the next thing that we see is there's really not a lot of change between these two time periods. I mean, the blue lines and the black lines are basically on top of each other here. So then, and if anything, in the southern region, there's actually an increase across those groups of plankton. So we can fit a linear fit to these plankton data and extend it out through the full size spectrum. And we see that we have slopes of about -1, which is what we would expect from ecological theory. And again, we see not a lot of change between these two time periods. Now we can focus in on the sizes where we would find bigeye tuna and look at how we might expect size structure to change just based on changes in the plankton community. We find that in the northern region, we would expect maybe a 5 or 6% decline in the abundance of large bigeye, and actually an increase of about 50% in that southern region that Kume looked at. And we just aren't seeing that in our data. So that begs the question of what might be driving these changes in bigeye size structure. And for this, we can turn to ecological modeling to try and tease apart the role of the environment versus the role of the fishery. So what you're looking at here, this is log of body mass on the x-axis. And along the vertical axis, we have the percent change in population from an unfished ecosystem. And then as you move from blue through green to black, that's increasing fishing mortality that impacts the ecosystem starting at this size. And what we've found is that if you hold the environment constant, you don't change anything in the plankton community, you don't change ocean temperature, and all you do is increase fishing mortality. You can drive down the abundance of large fish and increase the abundance of small fish. So this seems to suggest that the changes that we're seeing in bigeye size structure are a result of the fishery itself and not reflective of interannual variability in the environment. So there's still some questions to tackle with this work. Fishing practices have changed a lot in the past 50 years, so we need to dig in a little bit more and see whether that might explain some of the change in size structure. Also, these are just 2 time points that are separated by 50 or 60 years, and there could be a lot that's happened in between, so we're hoping to pull out some more historical studies and try and put some more pieces in that timeline to look at changes in size structure. Then the last example that I'd like to show you is looking at interannual variability at mid-trophic levels. So the 2 examples I've shown so far look at the very base of the food web and the apex of the food web, and it ignores everything that happens in the middle, even though that's really important stuff. So we're trying to get at those questions, and we're doing that using a fish called a lancet fish. So even though the Hawaii-based fishery is targeting things like bigeye tuna and swordfish, they actually catch more lancet fish than anything else. And these fish have really skinny bodies with this really watery flesh that's totally unpalatable. They have no commercial value. They're all thrown back overboard dead. However, they have really unique digestive physiology in that their stomach contents actually looks like this. And you can pick out individual species of fish, cephalopods, amphipods. Whereas if you look at a bigeye tuna stomach contents, it looks a lot like yours or mine, and it's really hard to tell what they just ate. Also, about 70% of the diet from lancet fish comes from these 7 prey families, and none of these prey families are dominant in our midwater trawls, so this is a great way to complement a lot of our oceanographic research cruises in the North Pacific. So we're starting to see what we can learn from this. First, starting with the lancet fish themselves, they seem to come in 2 size classes that we've creatively termed small and large lancet fish. They separated about 1 meter long. And there's very distinct differences in the diets between these 2 size classes of fish. So first, smaller lancet fish tend to eat smaller prey shallower in the water column. And large lancet fish tend to eat larger prey a little bit deeper in the water column. So we can get at questions about vertical structure in the ecosystem and across trophic levels. Large lancet fish also have spatial differences in their diet. So we can look at the impact of different oceanographic features on the food web. And then finally, there's seasonal variability in their diets. So for small lancet fish, their wintertime diet is separate from their diet for the rest of the year. And then for large lancet fish, their wintertime diet is separate from their springtime diet, which is separate from the rest of the year. So if we put all of these pieces together, we can start to look at things like the vertical propagation of the seasonal signal through the water column and look at how changes at the base of the food web and in the environment are moving through the mid-trophic levels and up to apex predators and help us piece together change across the entire food web. So our next step with this project is to start looking at interannual variability at mid-trophic levels. We have about 5 years of stomachs, and we're still getting them from observers in the longline fishery, so we can continue on with that work. So in conclusion, I hope I've shown you that our fishery really sits between both the spatial and the temporal footprints of interannual climate variability. So we really have to look for alternative drivers to explain interannual change in the environment and its impact on the fishery. So we've done this by looking at environmental linkages to recruitment pulses in the hopes that we could maybe develop a predictive capability to understand how the fishery is going to change in the future. We're looking at multidecadal changes in size structure for Bigeye tuna to try and separate out the impact of environmental change from the role of the fishery itself. And then finally, we're working on detecting change across the entire food web, looking at from the base of the food web through mid-level predators up to apex predators. And so with that, I'm happy for any feedback that you guys might have and ideas for other avenues that we could pursue. And I'm happy to answer any questions that you might have. Thank you for your time.
Thank you for a very interesting talk. Time for questions. There's one over here and then one in the back over there.
There we go. Hi, Andy Pershing, Gulf of Maine Research Institute. Really interesting talk. The shift in size structure that you report, this is something that's commonly seen, and I think fishing's a really good explanation. But you also often get changes in size at age and age due to physical effects. So temperature will tend to increase growth rates at young sizes so that you have more small fish, and then decrease growth rates later so that you have a smaller maximum body size. Have you looked at the size at age curves at all?
We have a little bit in the stock assessments, and so another piece then is looking at present day age and growth and then going back and pulling that from historic studies and trying to see whether that's changed. And also the fishery itself can exert changes on life history as well, so that's definitely one piece that we need to pull in there. Yeah, thanks.
Yeah, a little different question here. So I really was fascinated by your connection to these mesopelagic predators, these lancet fish. And you're putting a lot of effort into the temporal variability. I wonder, do you guys have any interest, or are you working at all looking at the spatial variability in the catch within the region? So not just, by a couple latitude bins, but looking a little closer, because in the open ocean, there's a lot of features that structure the ecosystems out there, and I'm wondering if you could pick out a very definitive link between what's setting where these fish are. And I'm sure the fishermen probably know about it, but you might be able to look a little further into the data you have.
Yeah, so in our initial work, we did try and look at the role of space, so latitude and longitude. We get the stomachs from the Longline Observer program, and so it's somewhat random where we get the stomachs from. So we can find the exact locations, but we can't control where we get them from. So I think over time, if we got enough stomachs, we could start to look at fine scale features. But in this initial analysis, beyond what they found for large lancet fish, they didn't find any significance in location.
Hi, Jessica Liu. I'm wondering, so you're talking about recruitment pulses of this Bigeye tuna. Have you looked at variability in the oceanographic features that might relate to their early life stages, like the larval stage?
Yeah, so that's another piece is sort of in thinking about what's driving changes in cell size and recruitment pulses is trying to figure out whether it's temperature, whether it's productivity, and teasing apart those influences, and we haven't gotten that far yet, but that's definitely one piece of the puzzle. Yeah.
Steinberg. I wanted to ask you about changes in some of these mid-trophic levels and from the sort of vertical perspective in the water column. So some of these fishes are feeding on mesopelagic zooplankton, and we have good time series in your area for the epipelagic, like the Hawaii Ocean Time Series, Station Aloha zooplankton time series. But unfortunately, we don't have long time series for below the photic zone. And I'm just wondering if you might be able to use the data that exists, like looking at night versus day ratios of zooplankton from the Hawaii Ocean Time series to look at maybe changes as an indicator of changes in mesopelagic zooplankton. So again, just a comment, there may be some data sets out there where you could, tease that out a little bit.
Yeah, it's a really good idea. Thank you for that suggestion. Thanks.
I think we'll take one more question before moving to the panel.
Mike, I had a follow-up question about the recruitment. Were you able to show that the prediction was better with the size, phytoplankton size index than with just chlorophyll concentration?
Yeah, so you're talking about that index of the small 15-kilogram fish? Yes. So that was a better predictor than just straight chlorophyll or temperature. Yeah.
Okay, I'd like to thank Phoebe again for a really interesting talk.